Okay, so we start with a platform of atoms and ions, and the presenter is from the LMU, is Tim van Lent. Thank you, and the stage is yours.
Yes, thank you for the introduction. So this will be quite technical talk, I think. We implemented recently a device-independent QKD protocol in the experiment that actually Christoph already mentioned before. So it's about the experiment where we entangle two single rubidium atoms. And in the end, I will also give a bit more information about things that we do within QRX, how we collaborate with other universities to really build or go towards this quantum repeater. Okay, this research is done together with our theory collaborators from the National University in Singapore, and also already want to note that you can also find the results that I'm presenting online. All right, quantum key distribution. Let's start with the goal of QKD. So what QKD wants to do, it wants to secure communication based on the laws of physics. And QKD systems nowadays are commercially available, as you see here. So this is the figure from Toshiba, where they have a QKD system over two cities connected via fiber link of 10 kilometers. And QKD the security is always based on some assumptions. So for example, that quantum theory is correct, that the users have freedom and secrecy of the measurement settings, which is done here via the quantum random number generators. And you also need to have secrecy of the outcomes. And I think if these were the only assumptions that were made, then I think QKD does a really good job in provide security based on the laws of physics. However, this is not the case. There are always additional assumptions that you need to make for QKD. So for example, the two users need to have perfect control of the quantum state that they have, and they need to have perfect measurement. Another thing is, and we talked about this yesterday as well, that there are always implementation vulnerabilities. So for example, you can make use of some dead time of detectors and then find some physical vulnerabilities of the system. And this gives rise to problems. However, as we also heard yesterday, the solution for this, the countermeasure to secure against those vulnerabilities is always also easy to implement. So just place an additional isolator somewhere, or just look at your single photon detectors if they're all working before you accept a click. However, you never know if you're secure against all different vulnerabilities. So then there was a proposal in the late 90s, and it is to do to introduce device-independent QKD. And in device-independent QKD, you can try to secure you secure the devices or the proper functioning of the devices also via quantum mechanics by the use of a statistical test, by a Bell test. And in this situation, you don't need to have any assumptions about the devices in the security proof. And this makes it device independent, and therefore you can also use it with uncharacterized devices. I want to state this. So what DIQKD wants to do, it wants to reduce the number of assumptions that are made in the security proofs. However, there are always some assumptions left, but these are fairly minimum for DIQKD. So I want to quickly go through them. So you need to have two devices that both receive an input and respond with it with an output. Alice and Bob, the two users, they decide when the devices communicate with each other. This is really important. And the devices do not send classical information to Eve directly. So on top of that, so those are specific for DIQKD, but for all QKD protocols, you also need to assume that quantum theory is correct, that there are trusted inputs available, that you can, for example, do via QRNG, and that you need to have an authenticated communication channel. Okay, so how can we realize DIQKD? What do we need to build such a system? For this, we need to have shared entanglement between two remote locations. And the quality of the entanglement needs to be really high because it requires a large violation of the Bell inequality to guarantee or to test the secure functioning of the devices. On top of that, we need to have a high detection efficiency, which makes it harder to implement with, for example, pure photonic schemes. Now here we have the resource that we need for that is provided by a quantum network. So if we have some nodes which are connected via quantum channels and we have shared entanglement between those nodes, we can use the entanglement there to implement the DIQKD protocols. And that is exactly what we've done here. So we use like a simple quantum repeater link to, for the first time, implement such a DIQKD scheme. The entanglement generation process is as follows. So we first generate atom-photon entanglement in our both nodes individually. By the polarization, we entangle the polarization state of the photon with the Zeeman state of the atom. Then we do a Bell state measurement, as you've heard before, and then we get a herald signal. This heraldic signal is sent back to the two traps, and at that moment we do a measurement on the atoms, or we start with the protocol. And this makes that the detection efficiency is effectively 1 in the system. Okay, so in the late 1990s or late 90s, this DIQKD idea was first proposed, and then in 2021, within 2 weeks, there are like 3 different experimental groups that say that they had a proof of concept implementation for the first time. So besides our experiment, there's also an experiment by the University of Oxford. So there's a nice experiment where they have a similar scheme as ours, only they use strontium ions to entangle, and they achieve a really high rate. So they can actually distribute finite keys. The only downside here is that those 2 experiments or the 2 traps are only 2 meters from each other. So that's also the reason why they achieve those high rates. If they would go to larger distances, the rates would go roughly or same order of magnitude as what we achieve here over 400 meters. And another implementation was done in China, and here they use entangled photon pairs. Okay, then a quick overview of the talk. So I divide the talk into 4 parts. First, I will show you how we generate the entanglement, and here I will go into a bit more detail than what you've seen so far. Afterwards, I will tell you which protocol we implemented and how we implemented this protocol, and I will come to the results. And in the last part, I will talk a bit more about the future plans we have, how we want to increase the distance of this quantum network link, and how we want to go towards finite keys, which require a way higher event rate. All right, then this is the quantum network link we're talking about. So this is the campus of the LMU, where we have the 2 labs, which are separated by 400 meters. The 2 labs are connected via fiber channels of 700 meters. This setup was used in 2016 to implement or to test or to do a loophole-free Bell test. Okay, what do we do in both labs? We trap a single rubidium atom. This we do as follows. We first generate a cloud, a cold cloud of rubidium atoms in a magnetic optical trap. Then we shoot in an optical dipole trap beam, which we focus down via this microscope objective. And the focus of the microscope objective is exactly at the position of the cloud of the mod. Then we can load 1 atom from the mod into the dipole trap. And now what is nice is that the atom that we trap is exactly in the focus of this microscope objective. So we use the same microscope objective to collect light from the atom, which we couple into the single mode fiber. If you would look there with a single photon detector, we would see a signal like this. If we see a low number of counts, we don't have an atom trapped. If we see a high number of counts, we have an atom trapped. And the second part is we want to generate atom-photon entanglement in both of our nodes. For this, we excite the atom. So this is the energy level scheme of rubidium. We excite the atom, and in the spontaneous decay, we generate the entanglement. And then the entanglement is between the polarization of the photon and the Zeeman state where the atom ends up. And this we do at 780 nanometer. And the second part is we do this in both of our traps. And then we want to do this 2-photon interference to perform the entanglement swapping to the atoms. For this, we need to have indistinguishable photons. And this we do by spatially overlapping the 2 photons using a fiber beam splitter. We temporarily overlap them by synchronizing the excitation pulses in both of our labs. And spectrally, the 2 photons also need to be the same. So we need to have the same frequency. And this we do by using the same transition in rubidium. So this the success probability of this process is quite low. So it's 10 to the minus 6. And this is only over a link of 700 meters, so 400 meters in distance. This is mainly because the collection efficiency of the photons is rather low. So the photons that are emitted by the atom go in the sphere, and we only have a finite Na that we can collect. However, we can do this with a repetition rate of around 50 kilohertz, such that we still get a rather decent event rate to demonstrate or to have a proof of concept demonstration for this DI. So what we do is we do a measurement on the two photons, and by this measurement, we herald an atomic entangled state. Then after generating this entanglement, we need to have a readout. How we do this readout, we have a state-selective ionization scheme. By shooting in first this readout pulse, and by the polarization that we set of this readout pulse, we can excite a superposition or a certain superposition of our qubits. And the superposition that is excited is directly afterwards also ionized. And then the next part is we want to check if our atom, so an ionized atom leaves the trap. And then we check with fluorescence detection, is our atom still there? Yes or no? And this gives our final outcome or measurement result. Now we needed to implement a few improvements to implement this protocol. So the first one was that we needed to increase the entanglement generation rate. This we did by changing the microscope objectives to increase the photon collection, and in particular to increase the amount of photons that we couple into the single mode fiber. Then the second part is we also needed to improve the fidelity. So before we had fidelities of around 80%, which are not high enough. And this we increased to 90% by accurately modeling the entanglement generation process. So we found out that, for example, we can have double excitations in our entanglement generation scheme. So here you see the photon detection time, and you see also the excitation pulse. And we see that while the excitation pulse is on, there can be a second excitation. So if you filter out those events, then you can increase the entanglement fidelity by roughly 10%. So what you see here is you see the start of the acceptance window. So we vary the part from where we start accepting the photons. And you see that if we make the acceptance window later, the fidelity goes up. The other thing that was important for us was that also on the theory side, there were some advances or improvements. And the improvements were that the critical qubit that we needed to achieve was increased. So therefore, it was easier to implement this, or it became a bit easier to implement this protocol. Okay, then next, the protocol that we implemented. So what you need to do for the DIQKD is you need to measure two things at the same time. So you need to measure an S value, not at the same time, but in the different runs. So you need to measure the S value to check the performance or to secure if the devices work as they should. And the second thing is that you need to measure the qubit. So for this, in the original protocol, Alice has 3 different measurement settings, of which 2 and 3 are used for S and the 0 for the qubit. And for Bob, there are 2 measurement settings. So 0 is used for qubit and for S, and the 1 is only used to measure the S value. The protocol that we implemented, as you can see, is a tiny bit different. We have an additional measurement setting for Q. And what this does, this makes it harder for Eve to eavesdrop the key. So what this effectively does is, if in the normal protocol, we assume that Eve always optimizes her measurement on Q on the used basis. Now we have 2 bases, so then in approximately half of the time, Eve does not have the maximum information. And by this effect, it became a bit less harder to implement, or the qubit increased slightly for the critical qubit. Then this is a schematic of our setup. So we have Alice in lab 1, then we have Bob in lab 2. The device of Alice is the single atom trap in combination with the Bell state measurement setup. For Bob also has a single atom trap together with a beam splitter here with which we reflect out a tiny bit of the fluorescence of the atom on this single photon detector. Both devices have an input. The input is the polarization of the readout beam, which I explained before. And the output of the 2 devices is the amount of fluorescence counts that we see on the detectors. And this is high when there's an atom present, and this is low when there's no atom present. So we get a binary output. So we do an entanglement generation tries, and then when these are successful, we send a ready signal to Alice and Bob. This ready signal goes to two QRNGs. So for Alice, we use we generate 2 random bits at that moment, which selects 1 out of 4 measurement inputs. And for Bob, we choose 1 out of 2 possible settings. These inputs are also stored in the local storage together with the output of the device. Now we needed to implement a few extra things to make sure that the system would not be too easily cracked, because we want to provide or show that you can gain security with this. And for that, we implemented 1 spectral filter here and a shutter. So these are there to prevent the input and the output of the device from Bob to leak out to the environment. So how we align this readout beam here is to couple it into the fiber that leaves the lab. So therefore we block this readout beam with a spectral filter. And the other thing is that if we do the fluorescence readout, if you want to see is this atom still there after a readout, then also some light will leave the lab. So therefore we first close the shutter before we start with this readout. And in this way we can make sure that both Alice and Bob's locations are secure. Then we come to the results. So what we did is we measured in total a bit more than 3,000 rounds of this experiment, which we did over a period of 75 hours. So the event rate is not yet where we want to have it, but this is a proof of concept demonstration. So we showed that we can, in the end, reach DIQKD secure key. So for Alice, we have the 4 settings, and those 4 settings you see horizontally here. For Bob, we have the 2 settings, and those 2 settings, this is Bob setting 0, and Bob settings 1 is the bottom plot. Then the points that you see are the correlation and anti-correlation probabilities. So correlation means the 2 atoms are still there. Anti-correlation means 1 is still there, the other not, or the other way around. And we can estimate the fidelity of the state by fitting those functions. And we see that we get a fidelity of almost 90%. Then we use the measurement settings with the green background, so those 4, to calculate the S value that we achieved, and the measurement settings with the yellow background, we can estimate the Q or the Cuber. So then what do you see here? Here you see the achievable asymptotic key rate for a measured S value and Cuber in this protocol. So where we want to be is we want to be in this region where we have positive keys. And this is what we measured. So the black point is the point, the data what I just showed you now. As a reference, I also show you here the data from the Bell test that we did in 2016. So you see that by improving the quantum network link, we reach the asymptotic or the asymptotic positive key region with a key rate of about 0.07 secret bits per entanglement generation event. Then what's maybe also nice to show here. So this is for the new protocol that we implemented. However, for the original protocol, we would also be within the positive key rate regime. However, so this is the boundary then, the 0 key boundary. However, we're a lot closer to the measurement to the point that we measured. Then the next step is, of course, you want to generate a finite key. We don't only want to show that we could generate a finite key if we would measure for weeks and weeks and weeks, but we, in the end, want to know how long do we need to measure and how can we improve this. So to find out how long we need to measure, we did finite key simulations. And what you see here is the epsilon security of the protocol. So this can be seen as like a probability that Eve still can eavesdrop the key because of finite statistics. And what you see here, is the minimum number of rounds that we need to achieve such epsilon security. So for in the QKD community, what people say is like you need to have roughly 10⁻⁵ here, and we would achieve that with 1 to 2, 10 to the power 5 measurements. All right, and then what's next? How can we go to longer distances? How can we increase this distance from 400 meters to kilometers or hundreds of kilometers? And how can we generate the finite keys? One important thing, and actually this is the part that Christoph did not mention, I think, in this talk. The next parts he did mention, but that is that we emit our photons at 780 nanometers. And at 780 nanometers, we have a lot of losses in the optical fibers. So therefore, what we need to frequency convert our photons from the near infrared to the telecom. Here you see how the event rate, the atom-atom event rate, will drop over distance. And you see that if you go to the telecom, we almost increase the distance or the reach of a quantum network link by an order of magnitude. So for this, we work together with the University of Saarland. And they built for us nice polarization preserving frequency converters, which have a high efficiency and a low signal to noise ratio. So this you have already seen. So what we implemented in both our nodes is such a quantum frequency conversion device. And we were able to, so the next goal is to really move one of our nodes further away. But for now, we were able to introduce fibers on spools and go up to 33 kilometers of fiber spools between the two nodes. All right, then what are the next steps? Next steps for us is to move one of our setups to Garching, to the MPQ. For this, we have two possibilities. So we for sure need to have this frequency conversion. But here I also come to the rate point. We need to increase our rate. And actually in the group of Gerard Trempe, they were able to increase the success probability by at least 3 orders of magnitude compared to the results that I've shown you now. And this they do by cavity enhanced interaction with the atoms. So they also use rubidium atoms, however, in a cavity to increase this interaction. And then there are two different schemes that we could propose. So we can do exactly the scheme that you saw in the previous slide. But another scheme, what we could do is we can frequency convert our photons and then frequency convert the photons back to 780 again at rubidium, and then we could store the quantum bit into the quantum memory enhanced by this cavity. If we get a heralding signal back, then we can do a readout at our atom, and then we generated atom-atom entanglement between the LMU and the MPQ over a fiber link. So we don't know yet how long the fiber will be, but the last figure we heard was 27 kilometers, which is already quite long, or will limit the rate that we can achieve. All right, then a quick summary. So what did I show you? We improved our entanglement fidelity that we can achieve. We implemented for the first time a DIQKD protocol, which we see that in the asymptotic limit, we are in the positive key rate regime. And I showed you what are our next steps. So including frequency conversion, we can go to longer distances, and that we are in progress of improving the event rate. All right, thank you.
Yes, thank you, Tim, for this nice talk about this. So we have now the 3 questions for you. So the first question is, what do you think will be the main use case for entanglement-assisted communication networks?
I think on the short term, then it's about security, that you can increase the security. So also, depending on my talk, I think for device-independent security, that is of course not short term. If you see the rates that we achieve, then there really need to be a few orders of magnitude improvement. But if you go to the normal QKD protocols, and then you do have these implementation vulnerabilities, but you can still make this more secure, I think, than classical schemes, because you have the different means to protect your information.
Yeah. Yes, and the next connected question on the path to realizing this use case, what is the main challenge you see in your field?
I think for us, it is now, I think the fidelities we can achieve so we go close to, now we have 90% atom-atom fidelity, and I think there's still room for improvement to go even higher. But for us, for our experiment, it is now the event rate. The efficiency to collect for us a photon from a memory is extremely low. And this is a big challenge. So for example, with the cavities, you can increase this a lot. So I think this is one step forward. But then also you need to, I think, go for some time multiplexing techniques to increase this event rate by another few orders of magnitude.
Yes, and finally, again, this question to the CG connection. So which possibility do you see for quantum technology to contribute to the success of 6G networks?
And so actually yesterday evening, I looked at some white papers from some companies, how they see 6G. And I quickly searched for quantum, but I could not find any notice of quantum in such white papers. But I think also to have like a whole general implementation of quantum would be maybe too much. But I think there are certain use cases. I think yesterday we heard a few as well between for some energy infrastructure, or to have some parts of the network that are really critical. If you can find there a nice use case, then I think based from there you can go to other use cases, or then you can build on that experience.
Okay, thank you. I think we have perhaps time for one short question before we go to the coffee break. So then thank you again for your contribution.